anti-damping torque. M is the local magnetization, sigma the polarization of the currents. And we have also, and there is also, we have, in fact, in the simulation, we have already introduced this one that is the most important. And the result can be also explained by the Thiele equation of motion. The situation with implant current is not so interesting. In fact, when the current in plane, one sees is that the motion exists only when there is a non-adiabatic term. So when beta is equal to 0, the velocity is 0. So the situation is exactly like for domain walls. One needs the small non-adiabatic term, what is not interesting. In fact, this is in contrast with the motion of lattice. With the motion of lattice, in fact, there is motion on a track like that. The motion finally is longitudinal. There is no transverse component. At the beginning, the skimmer goes a little to the side, is repulsed by the edge, and the motion is longitudinal. This suppresses one of the components of velocity, and this suppresses one of the terms of the Thiele equation, and it remains only the beta term. And so this situation is not really interesting. It's the same situation like for the motion of the main wall. The motion by spinal effect, by vertical current, is much more interesting. So you have seen this morning that the spinal effect can induce a vertical current, spin current polarized in this direction, in this transverse direction. And this is much more efficient. By introducing the anti-damping torque, one obtains even for relatively large value of alpha, this large velocity at very small currents. So this 10 to the 5th amps per centimeter square, which is small compared to the value for domain walls. So this is an interesting situation, maybe not for Gerashevsky model domain wall, we'll see maybe in the next talk. Okay, the motion is like this one, so goes, there is a repulsion. There is, at the beginning, there is a transverse motion, then repulsion by the edge, and the motion is along the stripe. What can be said also is that because this polarization is always transverse, that means that the skin can goes along a more complex circuit, turn with the circuit. What can be said? What we are trying to do, there is a theoretical problem that has been raised by some theoreticians, is as the motion, as the spin a mass in this motion. Is there an acceleration stage? And we have tried, we cannot see in this simulation any acceleration stage. So at least at the sensitivity of simulation, there is no mass or very, very small mass. In fact, the mass in the theoretical paper is related to some deformation of the skirmions in some type of motion that increase the DMR. But it seems that when there is only a linear motion, there is no this deformation. We don't see a deformation of the skirmion in the simulations. And it seems that in this type of motion, there is no we cannot characterize, identify a mass in the motion. Okay. What is, okay, no, this. Of course, the same simulation can be performed not only for a single skirmion, but a group of skirmion, like in this simulation, with the same velocity. You can see this one to the crosses on this slide. What I forgot to say is that the velocity is inversely proportional to the damping coefficient, that even larger velocity can be obtained by decreasing alpha. And in fact, this motion of group schema has been even a little more investigated by a Chinese group recently. And so they have studied as a function of many parameters the motion of group of skirmions to see if to find what they call a reliable spacing between skirmions, because there is a sort of repulsion between the skirmions, decreasing exponentially, but finally they found they have worked out what are the value of this reliable distance. You can see the distance can be of the order of 20, 25, 30, 50, 30 nanometers. This is so. Below the distance, the distance is slightly increasing during the motion. Pinning of the skirmions. We try the simulation of pinning by this notch with a larger magnetic anisotropy repulsing the skirmions to see what is the border between pinning and no pinning. And so these results are summarized. You can see the pin is not pinned because there is some flexibility of the trajectory. And in some situations also it can become elongated if, for example, when the distance between the notch and the other side is small. And finally, this is the result. This is the border between, as a function of the currents, pinning and non-pinning. You can see that for typical roughness, that is for notches of about a few nanometers, the depinning current is very small. This is less than 10 to the 5th amps per centimeter square. So this is confirmed what was seen in the experiments of the group at Munich of very small pinning of the skirmions. So application, coding information with skirmions. So there are several possibilities that you can imagine. First, this is, for example, taken from the site of the NEC company. This is an example of MRAM in which the magnetization of the bottom electrodes of the magnetic tunnel junction is shifted by moving a domain wall below in this layer. And so, of course, you can imagine in the same sort of device that you can replace the domain wall by a skirmion and move it to when the skirmion is below, this corresponds more or less to a zero magnetization, and when it is on the other side, the magnetization is maximum. So there is several possibility of playing this game, and using also the advantage of the skirmion that can be located in several places, more than a domain wall. Domain wall is more difficult to a skirmion, for example, for a triangle, the skirmion can be put into each of the angle of the triangle. The other question that can be discussed is, can be the skirmion interesting for the concept of racetrack memory that you know certainly. And so you understand easily what can be done, replacing the motion of domains by the motion of skirmions. And the advantage is certainly the possible, it's speculative of course, but the possible advantage of skirmions is that, in fact, I asked Stuart Parking what can be the ultimate spacing between two bits of information. He told me 50 nanometers. And of course, the spacing between skirmions can be smaller than 50 nanometers, and in addition, they can be moved by a smaller currents. And so, certainly, there is a possible advantage of skirmions, smaller spacing and weak sensibility to defect, and small current density. Okay, and so there is also interesting property of the skirmion, for example, this breathing mode, the generation of oscillation, etc. But I have not the time to discuss this aspect of the problem. And I proceed to the second category of spin-orbit effects. So spinor effect, Rashba effect, and motion of using practical use of these spin-orbit effects. Okay, spinor effect I will be very short because it begins to be well known. It's been discussed this morning by Bob Berman. So the deflection of the electron due to the spinor effect can be used to generate, to inject a spin polarized current into a magnetic field. We have seen that it can be used for the motion of skirmions, and this morning you have seen that it can be used to switch the magnetization of a small nanomagnet here. You have seen this morning this usual expression of the torque that can be obtained by the spinor effect. The parallel or anti-damping torque. M is the local magnetization, sigma is the polarization of the injected currents, and the field-like torque. And in fact, the important parameter is the spin Hall angle that now one knows for metals very large value of the spin Hall angle, as you have seen this morning. So this is all for the spin Hall effect. I proceed. What can be done with the Rashba effect at interface or surface? And you recall that at some interfaces, typically the best result that we obtain the interface between bismuth and silver, but at many interfaces of spin 2, you have this coupling between the spin and the momentum, spin momentum locking, that makes that the energy for a given value of K, there is a splitting of the energy for the two spin directions in the transverse orientation with respect to K. And this gives this sort of, for free electron, to this sort of dispersion curves. And finally, if you cut the system at the Fermi level, this gives these two Fermi contours for the eigenstate on this contour, this direction of the spin of the eigenstate, with different chirality for the two contours. And the best effects have been obtained now for the interface between bismuth and silver. And so what is the Edelstein effect and the inverse Edelstein effects? In fact, suppose that a current is flowing, you have an electric field, so that the current is flowing, that means that this contour, or one of the contour, is displaced in this direction. That means that you take out some spin with this direction, down direction, and you introduce new states on this side. That means that you introduce states on this side and you take out spins of the opposite direction. And so this gives rise, it has been said this morning, to a non-zero spin density. But of course there is a second contour, but it is smaller, but there is no compensation between the two because this one is larger than this one. And finally the result is a non-zero spin density, a spin-up accumulation up between transverse with respect to the direction in the current. What the inverse is the following: if suppose you inject a spin wide current, that is, you inject this spin direction and you extract spin with the opposite spin direction. That means that will inject a spin on this side, and you extract spin from this side, and finally, of course, and you have this situation. So we are creating a current. Of course, you are creating an opposite current for the second contour, because now you are injecting spin on the other side, this sort of spin direction, but there is no compensation, there is only a partial compensation, and the result is that injecting a spin current should give rise to a charge current in the direction transverse to the direction of the polarization. So this is to summarize the result. The Edelstein effect or Edelstein-Rabat effect, a lateral charge current induces a non-zero spin density that can interact with a magnetic layer or generate a spin current diffusing into adjacent layer. And I do not describe the theoretical work, for example, by Aurélien Manchon on this complication. And on the other side, the inverse effect, spin current injection induce a lateral charge current that can spread into adjacent layer. I'll show you a relatively simple and clear example of the inverse Edelstein effect that we have obtained by injecting, by spin pumping, a spin current at the interface between bismuth and silver. And so the experiment is that if the effect exists, it should induce a charge current, a horizontal charge current that can be compensated by a voltage between the two ends of the device. And so it works. In fact, this is a device, bismuth, silver, and permalloy. And in fact, so we try several types of them. First, spin pumping in silver. Only in silver, the effect was negligible. this corresponds to this in agreement with a very small spinel effect